We are going to see the thermodynamic derivation of phase rule. For that, let us consider a heterogeneous system consisting of C number of components distributed in P phases. That is, this heterogeneous system consists of P phases represented by phase 1, phase 2, phase 3, etc. up to phase P, and each of these phases consists of C number of components. That is, in phase 1, the number of components present are C1, C2, C3, etc. up to Cc, and like that in phase 2 the components present are C1, C2, C3, etc. up to Cc. This is the case this is the case for C4, phase 3, phase 4, etc. And in phase P the components present are C1, C2, C3, etc. up to Cc. This is the diagram showing the equilibrium between different phases. Phase 1 is in equilibrium with phase 2, which is again in equilibrium with phase 3, and this equilibrium continues up to phase P. Okay. Now we have to find the degrees of freedom F possible for this system. Degrees of freedom is the minimum number of variables such as temperature, pressure and composition that must be specified in order to describe this system completely. For that, let X be the number of variables possible for this system. That is, in order to represent the state of the system completely, we have to represent a lot of variables, and let X represents the number of variables that are possible for the system, and let Y represents the number of variables that is automatically defined. That is, in the case of triple point of water, there is no need to represent the temperature and pressure, because the triple point will exist only at a particular temperature and pressure. So like that, there are some variables that are automatically defined, and let it be represented by Y. Therefore, the degrees of freedom F can be obtained. We will get the degrees of freedom F by subtracting Y from X. Okay. Now, this heterogeneous system is in equilibrium. That is, the temperature and pressure for all the P phases in equilibrium are the same. That is, there is only one temperature variable and one pressure variable. T is a constant throughout the system and P is a constant throughout the system. Now we have to consider the case of composition variables. We said that there are C components present in phase 1. So for C components, there are C minus 1 composition variables are there. And since there are a total of P phases, the total number of composition variables possible are P into C minus 1. Therefore, the number of variables possible for the system X can be represented as X equal to P into C minus 1 plus 2, where this 2 stands for one pressure variable and one temperature variable. Another condition for the equilibrium between phases is that the chemical potential of each component must be the same in all the phases. Let us consider the case of component 1. The chemical potential of the component 1 in phase 1 is represented by mu11, and that in phase 2 is represented by mu12, and etc. up to in the case of phase P, the chemical potential of the component 1 in phase P is represented by mu1P. We have to consider the case of other components too. In the case of component 2, the chemical potential is represented by mu2, and the chemical potential of this component in phase 1 is represented by mu21, and that in phase 2 is represented by mu22, and that in phase P is represented by mu2P. This continues up to the component C, and in the case of component C, the chemical potential in phase 1 is represented by mu C1, and the chemical potential of the component C in phase 2 is represented by mu C2, and that in phase P is represented by mu Cp. So for each component, there are P minus 1 equations possible. Therefore, that is, this component 1 is distributed in P phases. Therefore, the number of equations possible for this component, this particular component, is P minus 1. There are a total of C components. Therefore, total number of equations possible or relations possible are Y equal to C into P minus 1. Therefore, the degrees of freedom F equal to X minus Y, where X is P into C minus 1 plus 2 and Y is C into P minus 1. Subtracting these two, we will get the relation for F as C minus P plus 2, and this rule is known as Gibbs phase rule.